All right, guys. How you guys doing? This is our last class before Thanksgiving. We have 2 classes when we come back, and then we have our first exam. Our third exam, maybe. That makes sense. Right now, what is your due date for your homework? Is this coming Sunday? Do you guys, would you prefer to have it due the Sunday at the end of Thanksgiving?
I don't care.
So like Sunday, like 9 days from now instead? Yes. I really recommend that you don't put it off to do it during Thanksgiving, and then you're traveling and like, oh, Dr. Bailey, I couldn't do it because I was traveling and I got stuck in the snow. I don't care. All right? If we're extending it 7 days, you guys have 0 excuses for getting it done on time. So what that means is that the post-quiz then will be the Monday you come back instead of sometime during Thanksgiving. It seems to make more sense that way. It doesn't matter to me when you do it. If it was me, I would get it done before I left so I could relax, actually kick back for a bit. And if anything, review for the exam this Friday or something. So totally up to you guys, but I will go ahead then and push the due date back until Sunday, the 27th maybe-ish, and then we'll figure that out. Okay, so let's dig into some more weak acids, and then we're going to start talking about buffers today. So Thomas, I hope you're calculating stuff and not texting people. Cool. All right, so go ahead and take about 2 minutes to answer this question. Okay. I'm Yana. Pick a different group to try and get.
This one is
Okay.
biology and that one is
Maybe back there with them or something? Okay. Keep working them. Seeing how you guys are doing. I really like when you're writing. That's very helpful. The only thing I would suggest is just to write just because it helps you kind of grab it.
I don't have a question about this, but at the beginning of the semester, I talked about exam how I was going to be leaving early on that Friday. So I should get on Monday. Do you want me to email you a reminder?
Yes.
Okay, so should I email you next week we get back?
So that's going to be a little bit tricky, so email me today and then as well when we get back.
Okay.
And the reason is because typically we do the scratch off and I release the results right away. I can't do that, obviously, if we're gone. So we'll figure out what to do.
And I think we just said that I would take it the Monday the Monday after that one.
Yeah, and you're going to have to promise me not to talk to anybody or hear anything about
Yeah.
All right, let's do another 30 seconds or so. Nope. Again? No. Yeah, last time you and Demetrius. It's just your group. Trouble. Come on, show me something.
You want to see work?
Okay.
Practice? But
We're talking about practice?
I want to show work. I don't have to watch out.
All right. I want to hear from, let's hear from Valerie. How are we finding pH of a solution like this? Okay. And what equation do we have for the rice table? No, what equation do we have? What chemical reaction do we draw out for? Because R and rice stands for reaction, right?
So, CH3CO2H reacts when
Let's be a little bit more specific. Justin?
H plus and H plus and C H3CO CO2.
So there needs to be a little bit more. What are we missing, guys? Brianna?
Is it the concentration of CH3CO2?
So we're not writing out the expression of Ka yet. So what is acetic acid reacting with?
Water.
So we don't include it in Ka, but it has to be there to describe where that proton is going. So then we end up with acetate and H3O plus. What's the expression, the equilibrium constant for this reaction? Alex?
It's the concentration of CH3CO2.
First of all, what's the term for it that you wrote above your arrow?
The equilibrium constant of the acid.
Great. So this is Ka. Ka is always a weak acid interacting with water that dissociates into conjugate base and H plus, or H3O plus. Okay? And then based off of this, we know that Ka is 1.8 times 10 to the negative fifth. Is that a strong or a weak acid? Why is it weak, Thomas? Okay, it's less than 1, so we know that this reaction lies to the left. And we know it's weak. Why else? Why else do we know that this is a weak acid?
It's not on the list of strong acids.
Great. Fantastic. Not on the list of strong acids. It sounds like a stupid response, but that is one of the best responses. And what's one other one? How can we look at this compound and know that this is a weak acid? It might not be an acid at all. If you didn't have Ka, how would we tell that this is a weak acid? Okay, so we could draw a Lewis structure. What would we tell from that? How does this help us determine that that's a weak acid? Why? Krista? Michelle? Katie? It's not just an OH. If you say it's an OH and that's where we end, then that's going to get you in a lot of trouble. So what is it about that OH?
Didn't you say that the ones that are carboxylic acids are always weak?
It's a carboxylic acid, not an OH. So an OH is an alcohol. If an OH is attached to a C double bond to O and becomes a carboxylic acid, then that OH bond is much weaker and it's much more likely to give it up. Remember we compared this to if we had ethanol and how the bottom one is not an acid and the top one is. And that all has to do with what that OH is attached to. Okay, so we know, I'm going to go clean this up a little bit. We know we have a weak acid. We know that many ways. And then we can do an ice table. What's the result of the ice table? You might have been doing enough of these where you might have just written out what the result of it is. So, Michelle, what do you have as the result from your ice table?
There's a K value, which is 1.80 times 10 to the negative fifth equals x squared over 100. There's the concentration of the CH3CO.
So why don't we write minus x?
Oh, is it minus x?
It is minus x.
Okay. I didn't do a table, so.
Okay, so anytime we do an ice table, if we don't do an ice table and we don't get this, we need to do the ice table. We need to make sure we do this. So then why is it okay to do what Michelle did, even if you did an ice table? Why is it okay to kind of get rid of this x on the bottom? Dan? We are going to assume that that's insignificant compared to that 0.100 molar. Okay, and then if we solve for x, someone want to give me the value of x they found if we did that assumption?
0, 0, 1, 3, 4, etc.
Okay, what is that? Claudia, what is that x we found?
And change the reactants.
Okay, the change in concentration of reactants, the change in concentration of products. So how do we use that? Why do we use that?
Plug it back into the table.
Okay, what happens when we plug it back in the table? Chelsea?
You plug it back into the table and you find the zero nature.
Careful. So we may or may not put it back in the table. Don, what are you thinking?
When you subtract it from the 0.100, doesn't it give you the PLH? And then you can subtract it from
So let's take our heads, zoom out a little bit. I feel like we're a bit too focused on where that number goes. So we said what that number is. One of the things it is the change in concentration The reactants went down this much, the products went up this much. Why did we calculate that X? It's also the concentration of H plus at equilibrium. If we wrote out that ice table, that is the concentration of this that's achieved at equilibrium. How do we use that then to find the pH?
Negative log of that number.
Negative log of the concentration of H plus gives us the pH, which is, what did you find, Michelle?
2.87.
Does everybody agree? Why not, Pat?
No.
Okay, so how many sig figs should we have?
3 into the decimal.
Okay, and then what did you get for that?
2.872.
2.872, I agree. 3 past the decimal. All of our significant digits starting out were 3 sig figs.
Dr. Bailey?
Yes.
When we did this in the pre-class quiz, and on the homeworks too, I've noticed, I keep forgetting that whole how many after the decimal point for the pH. So
I don't know if Sapling really cares about sig figs.
I've been using 2 sig figs and it still says I'm correct.
Yeah, so don't take Sapling's word for the fact you're doing sig figs right. It doesn't pay attention to it. It's up to you guys to make sure that you're doing rules appropriately. Okay, so we have 44% of us are on board. Sweet. Uh-oh. It's not good. Well, are we sure that that's even right? Is there anything we have to do to make sure that what we did was allowed?
We have to check the concentration of H plus. If the ratio of the concentration of H plus and the concentration of the original solution is less than 5%.
So careful. In this case, that numerically you're right. But we're not comparing the concentration of H plus to the original concentration of weak acid. What are we comparing to the original weak acid? X, which is the concentration of H plus, but that's not what we're looking at, right? Why are we looking at X? So it's a change in X. So when we were saying here, the thing that I gave Michelle a hard time about, this minus X here in the middle, if we're going to say we can ignore that change, then we have to go back and confirm that that change was less than 5%. So we have 0.00134 over 0.100 molar. What do we find? How many percent is that? I'll give you a hint. You don't need a calculator. 1.34%. Crazy good math skills, right? Hear from you guys. You're good. All right. Questions? This should start becoming second nature to you guys.
For the exam, will we have to just check the percentage for most of those problems?
You will always have to show me you check your assumption. If you don't,
Okay.
then you guys will not be happy with your grade.
Okay. Just wanted to know if we have to.
How do we check this? How do we make sure that these numbers actually made sense? Do we have a way of doing that? Brianna, what are you thinking?
I feel like it has something to do with Ken B, but I don't know.
Thomas, what are you thinking?
Just plug the number back in with the minus X
Into what?
into the K, blanking out what it's called.
The Ka expression?
Yeah, the K expression. Plug it back in, should be probably really close.
So if we go back to this Ka expression, let's try it. That relationship should always hold true. So if we put x in there and it doesn't give us 1.80 times 10 to the negative fifth, then we might have done something wrong. A lot of times people will maybe use the wrong value or divide or multiply or use the wrong exponent. So what happens when we plug that x value back in there? What do you guys get? Kirk?
I ended up getting 1.82 times 10 to the negative
1.82.
2.
Okay.
Just slightly off. But
Is that close?
Yeah.
Yeah, that's close enough. So remember, pH is a logarithmic scale, so if we're off by that little, I'm not worried about it.
If the number's the same, but your negative is different,
That would be a problem,
that's a problem.
because that means we're tenfold different or more. All right, so what we're going to do is we're going to start talking about what happens if we take that solution that we just discussed and we add something to it. So the common ion effect. So I think this is all the stuff worked out. This is the ice table. I'll post this online if you weren't comfortable with what we were doing. And so today, You guys are now going to start to predict the pH of a solution of a weak acid or a weak base in the presence of or base, in the presence of a common ion. And then we're going to determine pH of different buffer solutions using a Rice table or using Henderson-Hasselbalch. Did anyone try to use Henderson-Hasselbalch on that problem we just did? Did it work? No. Why didn't it work? There's no ratio. So what's the key in order to use the Henderson-Hasselbalch equation? What do we have to have in order to use the Henderson-Hasselbalch equation? We have to have the conjugate acid-base pair, and we have to have sum of both of them. If we don't have sum of both of them to start with, we cannot use that equation. It's a shortcut, and I'll show you how later today. Why it makes sense to use, but we can't use that unless we have both. And technically, we can't have any bigger of a difference than about 10 to 1. If we have 99% of one and 1% of the other, the Henderson-Hasselbalch equation doesn't really work. If we have a 10 to 1 ratio or 1 to 10 ratio or anywhere in between, then we should be fine. All right, and then we're going to be tying together acid and base reactions in buffers, stoichiometrically, talking about titrations. And that's probably something we'll do more when you guys come back. Okay, so we talked about this solution, right? 2.872 is the pH of this solution. So now the question is, how will this solution be affected if we add sodium acetate to the solution? So you can talk to your neighbor, try to figure out what's going to happen to the pH.
It's on PubChem. CH3.
You guys are really looking up acetate? Come on.
It's not one we use very often.
It is going forward. Did everyone take my advice and learn the polyatomic ions before class today? I was serious when I was talking about that. That we're going to be using a lot of them, and I see a lot of people looking this up. This is really a waste of your guys' time to do. Please just memorize them once, and then we'll be using them for the rest of the semester in any other chem class you have. Okay, everyone have their answer clicked in? So I'll just say that there is not an agreement. There's about a 3 to 1 consensus, though. Dana, what are your thoughts and why? Why is it a base? What's that? Why? Miata, what are your thoughts?
I'm not sure.
Okay, so if you guys are spending time on these kinds of questions, not sure, please raise your hand. I'm walking around to try to give you guys some feedback and input. Chase?
It's sodium acetate, so so it's the H3, it's the CH3CO2 minus, but has a sodium, so it's a salt. So when you put in solution, you're going to get the just acetate ion and then the sodium ion. And since it's a negative charge and it can receive a proton, it will act as.
So exactly what we did at the end of last class. I said you guys need to be able to go from the salt formula, recognize the ionic bond from the ionic bond, dissociate that and see what we have left. And then if you put that thing in water, is that going to accept or donate a proton? Is sodium going to accept or donate a proton? No. Sodium ions aren't going to accept or donate a proton. So then what about acetate, CH3CO2 minus? Why would it accept a proton?
When it disassociates with the ions, it's negatively charged.
So negative charge doesn't always mean it has to accept. It could accept or donate.
I just know I've seen the COO and then I've seen the COO.
Okay, so if we were to draw the Lewis structure, I drew that in the top right corner. You want to add to it?
Well, all the hydrogens
Great, so we can recognize that the bonds that are there with a hydrogen to some other element are covalent and they're stable, they're nonpolar. They're not going to separate in water. The only OH that was there would have been an acetic acid, which means that there's an H plus where that O minus is right now. So if we draw out a carboxylic acid without the H plus, we should really recognize that that is going to be able to accept a proton and form the carboxylic acid. So that means that we draw this interacting with water, we're going to guess that this is going to accept a proton from water and generate OH minus. What's equilibrium constant for that reaction? What do we call that? So that tells us it acts as a base. All right, so this one absolutely will increase the pH, which means that it becomes more basic. There's a couple different ways we can look at that. One of them is we're adding products to this reaction, which means it drives the reaction towards reactants, Le Chatelier's principle. The other way we can say is if we put a base in water, it's going to get more basic. It's pretty simple. Question? I thought I saw your hand. Okay. All right, so let's actually look at one example of this. So we have a solution now that is a mixture of both acetic acid and sodium acetate, 0.1 molar of each. I want you guys to find the pH of this solution. Yeah, so it's acetic acid, so it's still the same acid. So you guys have the Ka. And I want you to do this with an ice table. Try to do this with an ice table. We'll come back and do this later with Henderson Hasselbalch. I have tons that I want to get rid of, so if you want any mechanical pencils, stop by my Brown 177 office. People leave them behind all the time, so I have like 30 of them. You should just own it though. Like, I'm retro. Yeah, I'm a hipster. It's cool.
So I can start
Okay, so how much of this, what's going on here? What's your reaction?
No, that's what I don't know. So I didn't write it up yet. Is it this?
So what are these things? What is this?
This from the water.
What do you have in this solution? Let's just say it that way.
an acid. So
What kind of a compound is this?
the Na will be associated
Is it an acid or a base?
Oh, this is the acid.
Okay, CO2H. That tells us it's carboxylic acid. That means we donate that H. What kind of compound is this?
It's the base.
Oh,
So it's
Conjugate
the-
base.
Yeah.
Okay, so if we go back to your Ka expression, we have this and we have this. So let's write an ice table with both of those starting now for initial. And Dana, help to chat with the people around you just to see if we're all moving in the same direction.
So then, is he doing this right?
Yep.
But then,
But the question is, what direction is this going to go?
wouldn't it still go this way?
Why?
Because,
What was the K?
oh wait, the K is so confused.
So try to think about that. I think you can use rational thought to get through it. Did I just click something that made that show up? Or no? No, it's there. It's there. So is there something to start with? So write out a nice table. What do we have to start with? All right, guys, so let's talk about how we're setting this up. What would we do? How would our ice table look if this is the Ka expression? If that's our reaction, what are we going to put where? What's our initial concentration in our ice table of those things? What concentration? Don?
0.100
Is what concentration?
it's the same for both.
Okay, so if we wrote an ice table, can you show where that concentration would show up? Not Ka. We're not going there yet.
Sorry.
It doesn't. Unfortunately, that doesn't
Does
work.
not do that.
So you can
No.
undo with that thing. So if this is an ice table here.
But this isn't what we're doing. This doesn't have both of them.
Okay. So maybe if we do an ice table,
Oh, maybe it does. Maybe I'm reading it wrong. I had both of those as
so does anyone have an idea? Where would we put the initial concentration of 0.100 moles? Why did you put 0.100 molar for acetate? We don't have any acetate, right? We have sodium acetate. Great. So the first thing we need to say is what salts do we have? Those will completely ionize. Completely, right? It's kind of an over-assumption, but we say they completely ionize. And then just like any ice table, we start with a 0 for H3O+, because that's what we're trying to find. And we know that some of that is going to be released in the course of this reaction. Val?
So we don't care about iron at all?
In this case, does Na affect the pH? Nope. It doesn't donate a proton. It doesn't accept a proton, so it's a spectator ion. Okay? So then, Kristen, usually in an ice table we have X's, minuses, and pluses. Where do we put them? Do you guys agree? Pauline, do you agree? So how do we figure out which one's added and which one's subtracted? Kristen, are you comfortable with what you did and why?
Well, I just said KA. I don't know, I'm confused.
Who wants to help out? Michelle?
If we're using the same KA as before, it's less than 1, so it doesn't mean it's going towards the left, so it would be minus.
Careful, it lies to the left. It doesn't mean it's going. Going means from Q to K.
Okay,
So what's Q?
I don't know.
What's Q right now? Can we calculate Q? Concentration of products over concentration of reactants. What is the concentration of products? 0.100 times 0. Okay? Is our K 0? No, so we have to generate some products. So I agree with what Kristen wrote up here. Because there's a 0 there, we know that at equilibrium we don't have 0 for H3O+. So the reaction is going to go to the right to generate some of that. The question is how far? How much is it going to go to the right? So in the end, we have 0.100 minus x, it's not at all true, 0.100 plus x, and x. Alex?
Can you just say that there's 0.1 mole?
So this is all molarity.
Yeah, of acetate when there's Na attached to it.
Because as soon as it goes in water, we need to recognize an ionic bond between a metal and a nonmetal, polyatomic ion, and that those are going to separate. That's what we spent half of the last class doing, is we need to do that step first. And if we did that step first, we basically would say, well, this, in water, gives us, which one of those do we need to pay attention to? We don't really care about the spectator ion. So that means it's a 1-to-1 ratio. All of the sodium acetate became acetate in a 1-to-1 ratio, so we still have 0.100 molar of acetate. All right, so now how do we find the pH? You guys know how to do it now that we have the equilibrium concentrations, right? Go ahead and find the pH using the approach you've done before. and then click in your answer.
Isn't it the same pH pieces? It shouldn't be the same pH as that. We said it would increase. I don't know if it makes any difference.
Why would we?
So I'm just, did say that, we did say that, so I'm just. I have a question though.
What's your question?
I got the same pH as we did before, but if we said it was increase, shouldn't it be higher?
How'd you get the same? Where's your K? What did you do once you had this? Yeah. But then what do you use that to do? I need you to write out what you did to find your pH. No, don't just plug in numbers. You need to write out your whole expression. Ka equals, so do this expression again. It's not the same. That's why you need to write it out. All right, take about 30 more seconds. Make sure you have it set up and try to solve if you have time.
Oh, shoot. I was like, actually type it in.
And I don't just want to see Henderson Hasselbach. Michelle.
I did both.
Okay.
See, this is it right here.
All right. So what should our Ka expression be? Ka equals what here? Alex. What do we have for Ka equals? Great. So on the top is concentration of product, so 0.100 plus x times x. And then on the bottom? Okay, great. So this is our normal Ka. If anyone just plugged x squared over 0.100 minus x, you're forgetting that there's more in there than just the acid itself. So then the question I heard a couple of times is, so what about the assumption? McKenna, what are your thoughts? What do we do now? How we got here or what we do next? Claudia, what are your thoughts? So in the past, sometimes we ignored the plus or the minus x usually, right? Why? To affect what? Okay, so the big point is, compared to what we started with, it changes so little that it's not worth trying to do the quadratic to figure out how small that change was. It's not about that that number is small. We still need that number. It's just a question of when we compare it, we're subtracting it from something, or we're adding it to something. It might be so small that we actually don't even have any change at all. So, can we do the assumption here? What did you find, Brooke?
Well, we did the calculations with using the assumption, and we got x to be 1.8 times 10 to the
1.8 times 10 to the negative 5 is what you found?
Yeah.
Is that significant compared to 0.1?
Yeah.
It's about 1/10,000th of it. Is that significant?
No.
No, not so much, all right?
Oh, yeah, no, I didn't understand.
Okay, so we're going to ignore those x's because the change is relatively small. We know that the pH of this solution, even if it's a pH of 2, that's 10 to the negative 2, it's probably going to be a higher pH than that. So we can rewrite this equation as 0.100 molar times x divided by 0.100 molar. Val, how do we simplify that? X equals Ka. Okay, so what does that mean then? What's the pH of the solution? What's that?
The Ka.
pH is not the Ka. Is that out? Did you say that or?
I forgot to do pH, I just got X.
So what is the pH? pH equals pKa. Negative log the Ka, right? So our pKa is 4.745, and that's the pH of this solution. So what the hell? How does that make any sense? Chase?
You added a base.
Okay.
Personally, well, our first problem, we had a pH of, this is just my rationalizing, oh, this is probably correct. When we first did it, we had like 2.4 something was the pH, and since we added a base, the pH should go up.
Okay, great. So I completely agree. Big picture, we have base goes up. What else? Cosme?
Well, like looking at that formula, it's like the log of,
The Henderson-Hasselbalch?
yeah, if you do the log of that, it just ends up being 1.
So what Cosme is referring to is, let's write it out. So the Henderson-Hasselbalch equation is pH equals pKa plus log of the concentration of the conjugate base over the concentration of the weak acid in that conjugate acid base pair. If those are the same, A minus and HA, then what is that fraction? This becomes 1. Log of 1 is 0. So another way to confirm that is pH equals pKa when the concentration of A minus equals the concentration of HA. So let's think about that. If we have a drug or a compound of any kind, if I have an equal amount of the weak acid and its conjugate base and I put it in water, I know exactly what the pH is going to be. It's going to be the pKa. Or the other way around, if I know the pKa, I can tell you how acidic a proton is, how acidic an acid is. If something has a pKa of 1 and another one has a pKa of 7, which is a stronger acid? Why the one with the 1?
If the pH is 1.
If the pKa if these are for two different acids, and I ask you which one of those acids is stronger, the one with the low pKa or the high pKa, which one is a stronger acid? Pauline?
The lower one,
Why?
because it's a log function, so that means like we're taking the log of the pH, so the lower is going to be the stronger acid.
Okay, so I would turn it a little bit when we have a 50-50 mixture of the two, the weak acid and its conjugate base. There's a heck of a lot more H pluses out there for the one that has a pKa that's lower. About a million times more. 10 to the 6 difference in concentration of H plus ions. So let's check our assumption. Was it valid? So 1 times 10 to the 1.8 times 10 to the negative fifth, or Ka, divided by our initial concentration of either one of those to compare that change. And we find it is really, really, really small change. So our assumption was valid. So then let's talk about, we said we can check this, right? So does it check out if we plug everything back into Ka? If we look at Ka equals and we use the x value we found, does that expression give us back 1.80 times 10 to the negative fifth? Val, what did you find? It's pretty close, right? So 1.80 if we're using 3 sig figs times 10 to the negative fifth. So everything checks out. Or if we did the minus changes. Okay, so let's talk about the Henderson-Hasselbalch. How did we get this equation, and why is it so prevalent to use? So I want you guys to take a normal Ka expression, concentration of products over concentration of reactants. Remember Ka, not Kc. I want you to rearrange this equation to equal concentration of H+. So take a minute, write out how you can rearrange that equation to equal concentration of H+. So what does concentration of H+ equal for your rearrangements? So we're just doing simple math. We're just rearranging this expression to have concentration of H3O plus or H plus, whatever you want to call it, is equal to something. So Brian, how do we do that? All right. I think this is a lot easier than you guys are giving yourselves credit for. Katie, how do we do this?
You multiply the concentration of the HA, take both sides, so it crosses off on the right side, and then validate Ka times concentration of HA equals concentration of H plus times concentration of A minus, and you divide both sides by concentration of A minus.
Just rearranging this expression. I think it's a little clearer when I write it out this way. Okay? Concentration of H3O plus equals Ka times the concentration of HA over A minus. All right, now let's take the negative log of both sides. Go. What does it look like when you take the negative log of both sides? And if you're not so good with the rule of logs, ask the person next to you what you do about things that are multiplied or divided.
Doesn't it turn out, this turns out to be negative, this turns out to be positive, since it's dividing, so you're subtracting.
So we pull that out in minus.
Yeah.
Okay, so does everyone figure this out? Megan, what happens when we take the negative log of both sides? What do we have on the left side? Careful. Negative log of H plus is what? Negative log of concentration of H plus or H3O plus is pH. That is only equal to pKa at one mixture of the conjugate acid-base pair, so we're not generalizing that. Okay? So that's on the left side. What's on the right side then? Okay, so we can be a little bit more specific. So negative log of Ka. Is that Shane? Okay, so is it plus log? So it's plus the negative log.
Plus negative, so you flip them. Concentration of A minus over concentration.
Okay. So then, actually, I think I have it written out here. So if we have log of something times something, it's the same as log of something plus log of something. And since it's negative log of them, then that negative carries through. Okay, so on the left side of the equation, we have pH. What is negative log of Ka? So we have negative log, we have pH equals pKa. And then what do we do with minus log of HA over A minus? That's not the Henderson-Hasselbalch, right? Something's wrong. So if we invert these two, that changes the sign of the log. So if you're not comfortable with rule of logs and how you manipulate logs, that's something that you might want to pull a YouTube video up and play with over a break. Val?
Why was that necessary?
It isn't. So you can use either form of the equation you want, but the one that we see typically is the one pH equals pKa plus log of base, concentration of base, over concentration of acid. If you wanted to use pH equals pKa minus log of concentration of acid over concentration of base, that is totally legit as well. That negative sign inverting and flipping the fraction, that takes care of that difference. So what I was trying to show you is how the Henderson-Hasselbalch equation is derived. So if we put in any equation, anytime we have a mixture of weak acid and its conjugate base, or a weak base and its conjugate acid, so for instance, if we had 0.100 molar of each of these, what step is a Henderson-Hasselbalch equation doing that I've warned you guys about? If we just plug those numbers right in and do that calculation.
Just assuming that there's no change, I guess the x value doesn't change.
It's just making that assumption, right? It's making that assumption that that minus x or plus x is so small that we can ignore it. Is that always legit? Okay, so it pretty much is for every time that we have a 1 to 10 ratio, or anywhere in between 90% of one and 10% of the other, all the way 50-50, 60-40, all the way until you have 90-10 the other way around. Once you start having a really small fraction of one of the two components, you can't keep that assumption going. So this equation is only valid for a mixture of 1 to 10 all the way down to 10 to 1. You guys know what I mean by that? So if we had, could we use a Henderson-Hasselbalch if we had Henderson-Hasselbalch for this mixture here? 0.100 molar HA, 0.00100 molar A minus.
No.
Why not? So this is about 1%, and this would be 99%. We can't do that. We could do it if, however, we had a mixture that was 0.100 molar of the HA and That's about as far apart as those two values can get, because if they're further apart than that, then the minus x can become pretty significant. Does that work out for you guys? So is pH always equal to pKa? When is pH equal to pKa?
The ratio is 1 to 1.
Only when the ratio of weak acid to conjugate base is 1 to 1. That's the only time. It doesn't matter which of these equations you use, right? We can see that that cancels out. Log of 1 is 0, so it doesn't matter if it's plus or minus, it's still going to be the same number. I feel like I had a tablet somewhere. Could you guys derive this if you needed to? Okay, so what I want you guys to think about here is, depending on how strong the acid is, that ratio is something that we can calculate. We can back calculate at this certain pH how much of the weak acid is there, how much of its conjugate base is there. Is anyone taking the MCAT in the future? Raise your hand if you're taking the MCAT at some point in your life. Okay, so on the MCAT you will see questions about that. So lactic acid is an acid And the question would be, if you have a solution of lactic acid in your blood, right? pH is 7.40. How much of it's in the protonated form? How much is deprotonated? You guys can calculate that because you know the pKa and we know the pH. So you can figure these things out. All right, so let's have you guys do some calculations here and figure out. You guys want to use the ice table approach or the Henderson-Hasselbalch for buffers? If it was me, I would use a Henderson-Hasselbalch. Okay? So, check. Is this a buffer? If it is, let's use a Henderson-Dusseldorf.
Yeah, it's good. I just texted. I was texting my mom about it.
We have a special guest, guys. Dr. Wonkoff.
Hi.
It's my wife. Hello. Grab a seat. Join in.
Good luck. Hope whatever you're doing.
Oh, yeah. She can if you want. Does anyone want to write out their work? Thomas, you want to write it up?
Do I have to use the David Hasselhoff? Do I have to use that equation, or can I do the way that you
You can do the hard way if you want.
You can do the hard way. Alright, now I don't feel like doing the hard way.
You can do whatever way you want, man.
Dude, this is so fun to write with. Alright, yeah, so.
So what do you do? Just the game?
You gotta lay claim to it?
Yeah.
And then you just make sure.
Yo, real quick.
What up?
What is
Just keep going,
PK
dude.
is
You
what?
got it,
No,
man.
I don't know the equation.
I
PK
believe in you.
negative.
PK is negative log of Ka. Come on, dude. Come on, dude.
Alright, can you give me the values? Because I honestly didn't calculate it.
Huh?
I didn't calculate it. What is...
You have a calculator right there in your lap.
Yeah, but dude, he's gonna take it away.
He's gonna take it away.
No, you can't take it away.
Come on, man. What are you doing?
Done.
By the way, it's recording all audio, so just so you know, you're
Really?
being streamed to
Oh,
YouTube
shit. I
Action.
shouldn't have said that. Oops. What's up, YouTube? How we doing?
Alright, guys. So how are you approaching this? While Thomas is taking credit for all of his work, it's come along, but I'd like to hear how Megan solved this.
I use the formula pH equals pKa plus the concentration of the base and the acid.
Okay? And what did you use as the concentration of your base and your acid?
I did the concentration of potassium over the concentration of formic acid.
Potassium formate a base?
I thought
Tell me I did it wrong.
Why did you think so?
because the other ones were acid.
Okay. So on your worksheet, I gave you guys a structure in case you haven't seen formic acid before. So what would the conjugate base of formic acid be?
Basic things.
She's a basketball player. Formic acid. What's the conjugate base of formic acid? Is that Megan?
Without pH.
Okay. So if we're to write plus water. So like this?
No.
No, you're wrong. Alright.
The one on the end.
Yeah, here.
Carboxylic acid, that's the one, right? Okay, So that's our conjugate base. So then how do I look at this HCOOK? How does that relate to this at all? Michelle? So if I were to draw out HCOOK, this is what I would draw. Lewis structure, it has an ionic bond. This is HCOOH. This is HCOO minus. Once this dissolves in water, I have HCOO minus for forming. So we need to look at that. We need to look for all ionic bonds. Once we see our ionic bonds, if they're dissolving in water, they're going to separate. Then we need to say, well, is that an acid or a base? So Megan, what do you think? Do you still think it's a base? Conjugate base, right? It's this thing. I just like to make sure you know what you're saying. You're firm in your answer, okay? So that is a 1-to-1 ratio. We're assuming that all that potassium formate, a 0.52 molar solution, is going to give a 0.52 molar solution of formate, the conjugate base. And then our weak acid is formic acid. Concentration is 0.300 or 0.30 molar. Thank you, Thomas. So if we do the concentration of our base over our acid, and you found the pKa was 3.77, you took the negative log of the Ka value that you had. I like how you used 2 sig figs, by the way, that was good. And then you found that the pH is 4.01. Does that number make any sense? How do we check? How do we see if that number makes any sense at all?
I think I need help with my calculator, because I did that same thing, and I didn't get 4.01.
Did anyone else get 4.01?
Yeah.
Okay, so we can just work on that afterwards. Just
Say, you can turn the pH into the concentration of H plus, and then use that to see if the Ka value is the same.
okay, so we can go back and plug it back into Ka. That's one way to do it. What else?
I don't know if this is right, but there's more base than acid, so it's probably going to be more basic than acid. So it's going to be less than 7.
If it's more basic than acid. So you're onto something. Hold that thought. Can anyone help him keep going down that track? He had a really good thought there. He said there's more base than acid. So what should the pH be compared to what? It's not compared to 7. We're not comparing to 7 right now. What are we comparing the pH to?
It's just the formic earlier question.
What do you mean?
I don't know, this one.
So we're not comparing it to different acid. We don't care about that right now. What's that?
You could compare it to if you did like your pKa from that, and that would be your acid if they were both even, or that would be your pH value if they were both even. It should be higher than that.
Great. So what we want to do is instead of comparing to some arbitrary number for a whatever, not this compound, what we want to say is if we had an equal amount of the conjugate acid-base pair, pH would equal pK. So that means we have a pH of 3.77. We don't. We have more of the base than the acid. So Thomas, do you want to reframe your statement? So if we have more base than acid in this conjugate acid-base pair, the pH should be higher than what?
Should be higher than pKa.
Everybody agree with that? Okay, so we always have a frame of reference. We can always look back to the pKa to figure out what that reference point is and whether the pH should be higher or lower. Good job, Tom. All right, and I think I have this all written out. So we could do an ice table, waste all of our life doing this, or we could just do the Henderson-Hasselbalch equation because we have a decent amount of both of them. And so we do the Henderson-Hasselbalch. I got 4.01 as my pH for this mixture. We only have 2 sig figs, we should be 2 passidecimal. All right, so then let's have you guys calculate the pH of the mixture that is listed here as number 1. I think that's question number 7 on your worksheet. Go ahead and figure out the pH of that solution. Click in your answer. You have the data you need in the table. So make sure to try on your own. If you need a little nudge, raise your hand and I can come give you some ideas. Let's actually do this. How many questions do we have there? We have 3 of them? Can I get a volunteer for each of the 3 just to write that problem up on the wall somewhere? Who wants to volunteer? You don't have to have it done already. Brianna, you do one. Who else wants to do one? Nice and big so everyone can see it. Brianna, do your work on the wall, if you're okay with that. Who else wants to do one? Yep. Sabrina, thanks for volunteering. You do number 8, please. So Brianna, do number 7. Sabrina, number 8. We're running low on markers, but there should be enough around the room. And then Salma, do you want to do number 9? Kristen, can you, or Megan and Salma, you want to do it together? Yeah. Okay. So put it up beside that screen, please. And everyone else, try to work through all 3 of them. This is an easy space right here.
I haven't done 8 yet, because I messed up the last one. I took the wrong ratio. You got like 5.05, right? That's why I think you thought I took the wrong ratio. I'm checking myself out. The first thing I got was the 4.45. That would give you the
So what do we have here? How does that mixture up? Conjugate acid. So what would you like to have?
No, we're good.
That's okay. So do we have time to 90 ppb equals maybe 1% on the rate of all of that equals negative that
There's 2 ways to put the honey. You're doing KA and KV. What Sabrina's doing is what is this?
salt.
So PKW has that related to PKA.
However, if guys, we're gonna have calculus perhaps.
I mean, I did it the other way. It is?
Alright, I think we're getting close. So, has everyone just worked on question one, clicked in the answer to question one? So let's go ahead and ask Brianna to share how she worked through the problem that's up at the front of the room. Brianna, you're on.
So I just started with the Henderson Hasselbalch equations, and then I plugged in the pKa value for acetic acid that's in the table at the top, and then I added the log of the 0.25 molar sodium acetate over the 0.5 molar of acetic acid, and then
So in order to do that though, you didn't just use sodium acetate's concentration, right? What did you have to do to know that that was the base, the 0.25 molar?
I just knew it was the base. I don't.
So who wants to help explain that step? How do we just take concentration of sodium acetate and plug that in as a concentration of the base?
Oh, wait. Okay.
Go ahead.
Is it because when the sodium comes apart from it, it can't accept or donate a proton?
Okay. So then what are we left with?
Just the acetate.
Yep. So this is the concentration of acetate, not sodium acetate at the top.
Okay.
Because we know the sodium acetate dissociates 1-to-1, forms acetate and sodium. So that's why we can use that equation, because we know it's a conjugate acid-base pair. If we had formate and acetic acid, this equation wouldn't work, because it has to be the same pair with and without the proton. Okay? So then you have pH equals pKa plus log the concentration of the conjugate base over the weak acid. You did a very thorough job of adding all these things. And we found a pH of 4.45. How do we know if that's valid? How do we know if that's a reasonable answer? Chase?
You look at the pKa value,
Okay, so pKa is 4.75.
and you were adding more acid than you were base, so the pH went down.
Didn't go down. It's lower. It's more acidic than the pKa.
Yeah, the pKa.
Okay, so going means that it changed, and we just started out with this mixture. There's more of the acid than the base. That means that we're expecting the pH to be more acidic than the pKa, and hence why Brianna put this little itty-bitty minus sign right here. That minus becomes really important. And that's what falls out of this ratio, is whether we're adding to or taking away from the pKa. And one of the most common mistakes I see students doing during these calculations is they flip which is the acid and which is the base, and then you end up getting the wrong sign, and the pH will be on the other side of the pKa, as it should. That's why I'm really emphasizing that you think back afterwards, did my answer make sense? Okay, so we have 4.45. From what I looked at on the clickers, that was the most common answer before as well. So now the next question is, and I'm hoping that you guys are doing 2 sig figs. I don't know why this is not letting me select. There we go. The next question is the one that Sabrina got. How did you deal with that? So this problem is with ethyl ammonium chloride and ethylamine. So how did you deal with that? It's not like the other ones we worked with, right? Because you only have a pKb. Okay, so why do we do that? Why didn't you just plug in PKB? Okay, so hopefully when we looked at going from Ka equals concentration of products over reactants, and we derived the Henderson-Hasselbalch, you see that that Ka describes that relationship between acid and base. So you can't all of a sudden just plug PKB in. It doesn't work like that. So you, on your own, figured out you needed to do something with the group, okay, with help. And you figured out that you needed to have pKa instead. So here's the crazy thing. Does it matter if we're looking at a weak base as conjugate acid or a weak acid as conjugate base? What do you guys think? Does it matter if we're looking at a weak base as conjugate acid or a weak acid as conjugate base? Michelle?
Can you just write them in the log, like UPKB was the log with the base and the bottom?
So if you wanted to go through the steps that we did to derive Henderson-Hasselbalch, but do it for Kb equals, and then do that whole thing over again and find concentration of OH minus, you could do that, you would find POH, and I don't suggest you do that. What I suggest is it doesn't matter what we're starting with. As long as we go back to the Henderson-Hasselbalch, if we use the pKa, we will be able to find pH, so long as it's the concentration of whatever is the base over the acid. That this ratio, it doesn't say that this is the conjugate and this is the regular, or other way around. This equation holds true no matter which is the conjugate. As long as we make sure that it's base over acid, we use pKa, then that rolls out to give us the pH. Okay, so once you found the pKa, what did you find for the pKa? Okay, I'd want to see one more sig fig, I think.
It'll be 10.81.
10.81. And then you did plus log of? Which one's the base and which one's the acid? Is the base on top or bottom? Great. The base is always on top if you're doing pKa. And then from that, you can find the pH. Great. So you found the pH was 11.28. Does that make sense? Pat, does that number make sense? Why? Okay, so we have more of the base than the acid, so the pH should be?
Higher than the pKa.
Fantastic. All right, last one. The three of you guys want to explain what you guys did for the last one, which was sodium dihydrogen phosphate with potassium monohydrogen phosphate.
We use the Henderson-Hasselbalch and our pKa values in 321, and then we just found the base and the acid.
So before, the one thing I'd want to add to what you guys did would be to write out your conjugate acid-base pair. So you have, what do we have? Sodium dihydrogen phosphate. So we have sodium dihydrogen phosphate and potassium monohydrogen phosphate. If these things dissolve, we should have H2PO4 minus and HPO4 2 minus. Once again, memorizing your polyatomic ions. If you didn't do that, then these would make no sense. The names, right? Hydrogen mono or potassium monohydrogen phosphate. That these things kind of fall out of that. So which is our acid and which is our base? Shane? Acid has one more proton, has one less proton. Okay. And then once you have that defined, the rest of it became pretty straightforward, right? So that was really the crux of this problem. All right, thanks a lot, guys, for your effort. I hope you have a great Thanksgiving. I'll change the due date of the homework. And you have a workshop tomorrow, so don't forget about that. It's going to get you ready for the lab when you come back.